Okay, so we would now like to calculate what is the change delta Gn. So first of all, I'm going to look at this term over here with the log z. So if I write down what that term is, that's just e to the minus n over 2 log z. So that is nothing but z to the minus n over 2. I then have this green bit here. And because delta m is very small, I'm only shifting my scale by a small amount. It means that delta log z is also very small. So I'm going to expand e to the minus n over 2 delta log z to first order. That will give me 1 minus n over 2 delta log z. And then I will have the time-ordered correlatory y of xn onto naught. Now, notice that if I take the z to the minus n over 2 and I multiply by that sitting over there, that is just gn. Okay, so what do I get? I'll have 1 minus n over 2 delta log z times by gn. Well, 1 times gn is gn, so the second term over here must be delta gn. So this is the first formula that I get. Delta gn is minus n over 2 delta log z times by gn. Good. Okay, now, what we're going to do next is we're going to think about the Green's function in a second way and come up with a different formula for delta g of n. So, so this is the second point of view. So in the second point of view, do your matching. Do your matching. If you've done your matching, then Z and G and the cutoff have been replaced by the physical coupling and the renormalization scale M. So after matching, things only depend on G, P, and M. So do your matching. After matching, we've eliminated Z, G, and lambda, and Gn is now just some function of the physical mass and the coupling. So we again perform a small shift in the scale. So again, shift M goes into M plus delta M. And under this shift, we will find that the physical coupling will have to be changed. So it'll be the physical coupling plus some small change that we have to apply because now we're working at a different normalization scale. So what happens to G of n? Well, G of n will go into G of n plus delta G of n. And to calculate delta G of n is now a very simple problem. We've got a function of two variables. We want to calculate the first order change when we vary those two variables. And as usual, what does calculus tell us to do? It linearizes everything. So it says calculate the change because you shifted M, and then calculate the change because you shifted GP, and then add those two changes together. So the change, because we shifted M, is just delta M times by dg of n, dgn dm. And the change due to the change of the physical coupling is delta gp dgn dm. Well, here's a simple formula, a second formula for delta G. Now, this first formula for delta G and the second formula for delta G have to agree, okay? The statement that 1 is equal to 2 is the Kalan-Samanzik equation, okay? We have to rearrange it a little bit to get it into the form that it's usually written. So let's do that. So we've got delta M d G of n dm plus delta GP. Sorry, guys, I don't know why I said dm here. We're just applying the rules of calculus. So this is dGP. dGn dGP. So that's the change in G of n. And this must be equal to minus n over 2 delta log z g n. So the first thing that we're going to do is let's take everything onto the same side, and we're going to divide by delta m. So we'll get d g of n dm plus delta gp delta m dg of n dgp. And now we'll bring this over, so it'll become plus n multiplied by 1 over 2 delta log z over delta m g of n is equal to 0. Good. And then there's one more thing that's also usually done, which is that we multiply this equation by m. So I'm going to multiply by m. I'll put it in a different color so it's completely clear. There I've multiplied by m. Here I've multiplied by m. And here I've multiplied by m. And then we usually introduce a little bit of notation. So this m dg dgp dm, this is usually called beta. It's usually called the beta function. And this quantity over here, m over 2 delta log z delta m, that is usually called gamma. So gamma is usually called the anomalous dimension of the field. And we'll see why that name soon. So it tells us how the field changes as you the field strength changes as you change scale. And then this beta here, you'd usually say beta function. So people talk about the beta function for different theories, and we'll see how to calculate it. So this is now the Kalan-Samanzik equation. So let me just copy it out again. In fact, I'll write it out again. So this is how we would usually write it. M d by dm plus beta d by dgp plus n gamma acting on gn is equal to 0. And let's just remind you that gn was the endpoint function, the endpoint correlation function. So let's just rescue this formula. Let's just put this downstairs to remind ourselves of exactly which correlator it is that we are calculating. Okay, good. So there we go. Okay, so let's make a couple of comments. This is a pretty remarkable formula. You see, what correlation functions in the theory could we consider? Well, in this 5-4 theory, correlators of any even number of fields is non-zero. So we could calculate G2, G4, G6, G8, and so on. So an infinite number of different correlation functions. And the claim is that they all obey this equation that I put the black box around. This, by the way, is the way that the Kalan-Samanzik equation is usually written. So this would be the Kalan-Samanzik equation. So all of these different correlation functions would obey this partial differential equation, and it's entirely determined by two functions, beta and gamma. And so what you could imagine doing, imagine you calculate, say, the 2-point function. We'll work at recoupling. So let's say you calculate the 2-point function to one loop, and you calculate the 4-point function to one loop. You can take the 2-point function and 4-point function, plug them into this differential equation for n is 2 and n is 4. And then requiring that these differential equations hold, you'll be able to determine beta and gamma. And once you've found beta and gamma, you could go away and check, does the 6-point function obey this equation? Does the 8-point function obey this equation? And so on. And in fact, all of the correlation functions will correctly obey this Kalan-Samanzik equation. So that's pretty remarkable. And calculating beta and gamma are very interesting. Beta tells us how the coupling constant changes when we change the scale of the theory. And gamma tells us how the field strength changes as we change the scale of the theory. So changing the scale of the theory will change both the coupling as dictated by the beta function and the field strength as dictated by the anomalous dimension. What we're going to do next, we're going to calculate beta and gamma. So you've got an example of how to do it. It's always done in exactly the same way. And then we're going to spend a little bit of time building up some interpretation for the Kalan-Samanzik equation. And I really want to prove to you that beta is telling us about how the coupling changes as we change scale. And I want to prove to you that gamma is telling us about how the field strength changes as we change scale. We'll do that in a moment.